20 minutes, no more. Lecture number 4. So lecture number 1, we discuss stochastic processes. Why this is important? We discuss this. It represents quite a bit of problem in biology, and you need to understand how to manipulate. What's the problem? You have a process which is a random variable. How you calculate something with a variable, which can be Ito calculus, which can be estimated the probability density function, associated first passage time, the time to reach a threshold, which is a key process in finance, in biology, in anything which carries stochasticity. Then we saw in the second class some calculation, and then we moved on up to now to development. And now, before going into neuroscience, I want to discuss some tools, not all, it's huge, it should be an entire class. I want to discuss some tools to study time series. Time series are what? This is an example of a person carrying an electrode mask, an electrode array. From each electrode, you can get time series. From this time series, you want to extract features. And the question is, how do you extract features? What do you extract? What do you need to extract? And where the code is? Where is the coding information? I think you all know that if you have a series, which is periodic or not, you can, so if it's fully periodic, more than 200 years ago, Fourier showed that this is what you should have known at school. Every periodic function can be summed as a Fourier series if it's periodic. And then what Fourier understood is that you can calculate the coefficient with respect to the function itself, and it's just given by this, because if you integrate and you multiply by the exponential with the k, you are going to kill all of them except the one with ck, and then you get ck as a function, and that's how he proved it. And then hundreds of years later, people have been looking at, in which condition you have convergence of the ck, what are the regularity, you can have functions that are very oscillating, and that leads to very slow or very sharp, and then if you have even discontinuity, and then it leads to all kind of phenomena, including Gibbs phenomena. If you want to represent a square, which is a periodic square, at the square, it doesn't converge well, because what you are interested in is not to have a series that goes from 0 to infinity. Because if you do numerics, you have to truncate. Let's say k from 1 to 10. Is it good from 1 to 10 or not? Maybe you need to go to 1 to 11, or 1 to 1,000, or 1. What defines n? So if you have this Gibbs phenomena, this has been known for 100 years, you can have oscillation at the boundary, and more you increase n, and less you get this oscillation, right? So I mean, just to make sure that you understand what I'm talking about, right? If you want to represent let's say, you have a square function, this is your space, this is time, for example, or whatever. You want to represent this by a series, Fourier series. What is the difficulty? The difficulty is that it will approximate this, but here it's hard, so it will oscillate. Because if you truncate the sum from 1 to 100, let's say, of, let's say, sine n t divided by n, or something like this, I think this is a representation of this, if I remember correctly, it converges slowly, and if you plot this, you will see some oscillation, and if you add more of terms, you get this oscillation that gets smaller and smaller. Okay, so associated to this is the notion of reconstruction of a signal, of the notion of how many terms you allowed yourself also to transmit information from telephone or satellite. And if you take a lot of terms, you get a very accurate signal, but it's going to be expensive in the communication. That's the theory of communication, the theory of cellular phone, the theory of how to transmit for television, and it went to this, then to JPEG, and all of this is based on the idea of how much you want to represent. But do we care about this in neuroscience? In neuroscience, what we are interested in is to understand the signal, not necessarily to transmit the signal, or not to have necessarily to use this to represent, but this to do some messaging like filtering. Okay? So, for example, this is what I just discussed, but most of the time you don't have necessarily a stationary signal. You don't have necessarily a periodic signal. And so what is the method that has been developed for this is instead of going to the discrete sum, you go to the continuous, which gives to Laplace transform of the signal, where you have, let's say, a signal f, and you can take a sliding window, which can be this j. And so you have your sliding window, you have, this is the time, and outside the window everything is 0, and then you have your signal here. And so you take a piece of a signal on this window, and then you can integrate. So if you integrate from 0 to infinity, doesn't leave much, except that you're doing a convolution, so it's a little bit bigger than this interval. This is how you do convolution. And you get a result. And so this is what people, this is the basis of, you have a signal, you take a sliding window, and on this sliding window you do a Fourier transform. You all know what is a Fourier transform? Right? So you take your signal x of t, and you multiply by a omega t dt, and you integrate. So if you have a window between, let's say, you integrate, let's call it s ds, and you integrate between t and t plus delta t, and you can for example, normalize it by t with a 2 pi whatever. And if you take this is called your Fourier transform of your signal s with respect to omega. And what is interesting to calculate is the magnitude square. This will give you what? This will give you the information of the power, of the energy for a frequency. For example, if you have a cosine, this is in the time domain, just to make sure that you follow, with a frequency of oscillation, let's call it omega 0. What do you see in the frequency domain? A Dirac at omega 0. You know, and if you have a certain amplitude, you can see here that your amplitude square that is coming. Is it clear for everybody? This is the basic of Fourier, what you learn at school, no? Great. Now, if you have a mix of something at 2 omega 0, you get something at 2 omega 0. And if you have something which is more, you can sum all of these events. So you have something at omega 3, you get your omega 3 here. So you compute the power on, so you take x, you calculate the Fourier, that's what we just discussed, and you calculate the Fourier squared. And what you see on the signal that I'm showing to you here, you see this. What does that mean? When you see this?
The signal is not periodic.
Yeah, it's not periodic, that's for sure. You can see it from here. You don't need this.
No, it's not a Dirac, it's
yeah, it's because the process is smoothing, because this is now you use the classical algorithm. You can use fast Fourier transform that you should have studied. What do you learn from this? Okay, there are many things we learn. First of all, this is the low frequency. So the low frequency, what is the low frequency you see in the signal here? Where is the low frequency? It's here. You have something like this, right? That's the low frequency. Where is the high frequency of the signal? It's here. That's the high frequency. So the high frequency is here, and the low frequency is here. So there is a decay, as you said, and there is a peak. Where is the peak? Around 12, there's a peak, which means at 12 Hertz, you can see here, so if we magnify a little bit, if we magnify these things here, although it's not very clear on this picture, you will see something at 12 Hertz. 12 Hertz means during 1 second, you have 12 oscillation. Is it clear what I'm saying? So this is a way to say that, but the power in the signal is where you have high amplitude. It is mostly for slow oscillation. The slow oscillation carries the power, and that's as the frequency is increasing, you see a decay. But it's not an absolute decay. Here there is something that is popping out at 12 Hertz. So that's what you get. So for example, you can ask, maybe there is a tendency here of decaying. Maybe I can fit here. So this is in, this is, okay. This is frequency. So you can say maybe there is here a power low decay. That is, maybe you can say I can fit a curve. Fitting a curve, you know what it is. You take a function, let's say 1 over f power alpha, and I have 2 parameters, and maybe I can fit here a decaying function. And so what could be interesting is to get the information about those 2 parameters, A and alpha. Okay, so this is the fitting of the power spectral density, and we get 2 parameters to estimate, A and alpha. Is this important? Is this interesting? Yes, in some cases, because we can think that it could lead to, it could give information about how the different frequencies are organized. So this is an example of traces obtained during anesthesia. This is human anesthesia. And during human anesthesia, you see this type of behavior. There is a power and there is a peak. So another question of interest. What could you be interested in? You can say, look, fine, you can estimate this. But you can say, why not focusing on this? Why not saying, I'm also interested in this? Can I say something specific? For example, I can say, right, I want, if there was no such a thing, maybe things would be like this. And then you could say, I would like to extract the characteristic of this feature based on this baseline, that abstract baseline that I will obtain by just continuing this. And then I could say, all right, I can get some information about the amplitude here. So this is, I'm explaining now to you how you can segment in the space of frequency. You go to Fourier, you get power spectrum, you see, for example, could you see this in this? The answer is no. You have to do this power spectrum analysis, Fourier transform, to extract the peak, to extract the decay, and maybe also to extract, and if you say that there is also, you continue here, maybe also there is something interesting, maybe there is here another peak of interest. And this second peak of interest, here it's actually associated with what is called a delta frequency, which is a frequency between 0 and 4 Hertz. This is associated between a frequency between, let's say, 8 and 15. This is called the alpha frequency. And so you can say that, look, maybe there are things to extract here just by looking at these statistics. It's elementary, it's Fourier analysis, but now you can see that there is features to extract. Okay, so this is an example of application of Fourier. Yeah, so this is the same. You get a more ugly signal coming from Pierre-Olivier. Ask him to give me, in the rush, this is a signal. And what do you see? Yeah, the scale is not very clear, but you see a first peak in here. You see the peak, and you see a second peak here. So and a decay. So this is the decay. There's a peak, and there's quite a bit of fluctuations in the power spectrum. How do you reduce a fluctuation in the power spectrum? I'm not talking about, how do you, if I want to have on this signal, I want to reduce the power, the fluctuation.
You can convert to Gaussian kernel or...
Yeah, or you can increase the time window where you do your analysis. Okay. So again, you see two bumps, which can be used to characterize your signal. All right, so this is the power of the Fourier analysis. Okay, so let's move on. What happens if now you take the time series, you have a window, and you compute your window over one position, a second position, a third position in time. So you have time. This is what happened: time t1, t2, t3, and then you need a way to represent all of these. I'm not going to show 1,000 picture. I want to concatenate them. And what you do is a spectrogram which looks like this. The peak here is the peak that you see, the red. The decay up above here, this is the lower frequency. This is what you see here. And when you go far away, so I take these slides, put it like this, and each time you see this. Now, when you have a signal like this, it's one thing. When you have a signal like this, it says, look, in this signal, I see that there are a lot of power between 0 and 4. There is nothing here, and I have the impression everything is continuous, and I have a second power at 10 Hertz. And then at some point, things start to change, and we know that during anesthesia, this is associated with the moment where you stop giving the drugs. When you stop giving the drug, you see that you can read that you have here this opening. So the Fourier analysis, this has been used for 20 years in commercial devices that allows you to read and to understand what you see in the signal with this time frequency representation. So you read immediately that there are two frequencies, that this frequency, you can see how they evolve in time. Right? I'm going very fast, but I think it's clear. Once you understand then you need to program this. You need to write the algorithm that from this you do the Fourier transform, and it is actually done for you. There's a function in MATLAB, in Python, that do it in one line, or maybe two. Okay. However, sometimes what you see in the signal is there are features. Because, look, this is the resolution of the machine. And the resolution of the machine shows that you have like a very continuous line. It's very red. But now, by changing the time scale of your analysis, instead of having hundreds of seconds, if you go to few seconds, suddenly you see by eye that there are features in the signal that appears like here, this kind of fast oscillations, which are represented here by these events. You can see here these oscillations that are represented by the red. So this is one more step. One more step is that the time at which you look at a process is fundamental. And this is not given by and you have to decide. You have to decide. You have to decide the right timing. And this is hard, because you have to try. It took us a couple of years to understand that this is an illusion. This is an illusion. There is no science here. This is an illusion of the graphic because of the time scale. And if you increase the size, you get something which have a sense. This is called spindle. This has a name, and they have there's a beginning, there is an end, and when you do the power spectrum, you see this peak. So the message here is that the time resolution can be fundamental for studying a process using Fourier. And you don't have to do anything just to get this right representation, because this allows you to do segmentation. Do you know what is segmentation? Segmentation is to cut. You have your scissors and you cut. I want to extract this. I want to know where this starts and where this ends. I want to do it automatically. All right. So now that you perceive what you have to do, it's much clearer how you do it, how you have to do it, because you understand what to look for and how to write your algorithm. So, okay, you can take this, for example. You know what is filtering? Do I have to explain a bit of filtering theory, or is it clear? I don't know. It's you don't be shy if it's not clear. A filtering theory is, I want in the signal to remove frequencies. So, for example, if I have this and I want to filter on this band, so I want to remove the signal that is here and the signal that is there. You know, you can use what is called a pass band filtering. Yeah? So this means that you remove from 0 to, I don't know, to 8, and from 15 to, so this is called a pass band. And so you can filter, and instead of having everything, you get just this little band. And this is another representation of the signal. This is the same signal filtered. It looks different. It's normal because you filtered. You remove all this fast component and this slow component, and you see beautifully appearing some structure. So filtering at the right frequency, here we understood that this was the frequency of interest. You see specific features. For example, you can count even how many you have. 1, 2, 3. Maybe this is not important because they are lower than the threshold. And you can count. And you can count the peaks. And the algorithm to count peaks. And this could be interesting because then you can quantify how many of these spindles you have during a certain amount of time. So the time scale is fundamental. Okay, there is also another thing that is important. I show you that there is this event. I just showed to you the slide before. There are those events. The events are characterized by a certain frequency. 10 Hertz, they are oscillating. And so when you look at it over the signal, you see this peak. Fine. So there is something to calculate on the signal which is interesting, is what is the instantaneous frequency of the signal. If I have cosine omega t. Cosine omega t, I can see it in the complex plane as the real part of exponential I omega t. What is the instantaneous frequency? So if I write this real part of exponential I phi of t. Phi of t is a phase. So phi of t is omega t. So how do I get the instantaneous frequency? It's d dt of phi, which is d dt of this, which is omega. So at each time t, I know that I'm oscillating with frequency of omega. You understand? This is, now I want to generalize this. I have a complex signal, and I would like to ask you, what is the frequency at this point? How do you define the frequency at one point? Well, I show you the method. That's the method. I have a signal x of t. And if I can put the signal, so I have to add something. And suppose I can do this and put it in the form r of t exponential phi of t I. How do you define the instantaneous frequency? What? Yeah, so you get exactly, so I can define omega at time t. Maybe it is constant. This is the case. It is constant. Omega at time t is going to be defined as d dt of phi of t. And if phi of t can be expanded this way, you understand that you're going to go back to omega. All right. What do I need to add here? How do you construct this? For cosine, it's easy. You all know that cosine plus I sine omega t is equal to this. So what is the function that you have to add? This function is you shift it from pi over 2, sine and cosine. This is elementary. And that's what Hilbert transform is doing for you. You take your signal x, you calculate this Hilbert transform. If I do Fourier of this, you know the Fourier of the convolution will give you the product. This is the sine I is pi over 2, you know I is can be written I pi over 2, no? You all know this. So this is a shift of pi over 2. You have a function x, I do the Hilbert transform. This is classical theory of distribution if you have studied distribution before. You do this transformation, you see that this is exactly I, you multiply I and sine omega. If omega is positive or negative, it gives you, there's a sign, which is minus 1 if it's negative, plus 1 if it is positive, and then you have the Fourier of the function x. So this is the Hilbert transform that you have to put here. And then you can put it in this way, and then you can calculate the instantaneous frequency. And this instantaneous frequency can be complicated. We don't know what it is, because if it's a sum of many things. But it's interesting that you can do this, because you have now a classical representation in amplitude and phase. And you can represent what is the amplitude R. What's going to be the amplitude R here? What is R? R is the if you have R will give you information. So if you have R of t, if you have a complex number, it's x squared plus y squared, no? Square root, that's the definition. That's the distance. So this would give us information about how the signal, the signal, the envelope of the signal oscillates. And the phase is going to give us information about the frequency. Okay, so this is important because this is a nice representation of a signal x when you can map it into 2D, although it was 1D by this trick. It's a trick. But for cosine, you knew the trick because you knew that it is associated to a function. And that's the way to do it. Okay? Okay, I'll stop in a second. Yeah, so this is reverse. Yeah, no, so this is more complicated. So I will discuss this next week about how to recover parameters from different things. So this I want to skip. I just want to go to one. I'll discuss this next time. I just want to finish by this. A different algorithm to represent function. This is called empirical mode decomposition. Have you ever heard of this? The empirical mode decomposition is a way to decompose a signal. So suppose you have a function like this. The empirical mode decomposition is a way to represent the signal by identifying a local minimum of x. And so you look at the maximum, the minimum. You interpolate the local maximum to form the upper envelope and the minimum to go the lower envelope. I just follow the rules. So I do this, and upper envelope, and I want to do the same with the lower envelope. So this is called x up, and this is called x lower. Compute the mean envelope, m1 of t. So what do? I take x up plus x low, and I divide by 2. I subtract the main envelope from the signal. That is, I call it x the signal, and I do x of t minus this. And I call it h1. And then what you do is you start from h1 and you repeat the algorithm. So h1 subtract, check if f1 satisfies the EMF condition. If it does, h1 is the EMF. It does not, repeat the process. The results of this process yield to the first EMF 1. So I don't discuss what is the EMF. Let's suppose now we repeat the algorithm. We will see when to stop. Now I have this. What do you get? Suppose you remove this envelope. I'll show you in a second the result. What is your intuition?
Make it smaller, the amplitude should decrease, right?
The amplitude should decrease, but what are you getting rid of? That's right. So if you have this big envelope, if you remove it, you get rid of this slow type motion oscillation. So let's see what we get. This is a signal. I remove the envelope, upper and lower. First iteration, you remove the low frequency. What you see, you are left with it's like stretching everything, so you have no anymore this slow oscillation. And then you repeat this on this. Well, again, so there's oscillation, and here there is so when you do this, you get some information about the signal from here, and when you remove, you get your signals after all this iteration. At some point, if you do this, it will remain nothing. So at some point when, for example, the variation is smaller than something, you don't care. You stop. And that's what you get. So this is a way. So I want to show you this on a better example, which is a real case problem, which is called absence crisis. This is called an epilepsy crisis in children. What do you see? You see that there is an oscillation signal, and you have a motif which is a spike and a wave. You have a spike and a wave. Something that is very sharp and something that is very smooth. And you want to identify this automatically. That's your goal. Okay, so this is an example. You get different electrodes. I want to identify this. Okay, so this is your signal. As I said before, what is important in this is to find the right scale. At this scale, you don't see, you just see these events, and when you open the scale, you see this event which is not normal because of the spike. Right, when you have identified the scale, you are interested in trying to make a segmentation. For example, you want to identify this feature. So we try different motifs. For example, here you have a certain absence crisis, another absence crisis, and we can tell that if the distance between the two is not too large, you want to say this is the same event. Then we said, okay, maybe it's interesting. This failed. I'll show you things that fail. This is interesting when it fails. You learn when you fail. That's why it's important to fail all the time and to recover immediately. That's what I taught my children. You have to fail, it's okay to fail all the time, but to recover. Like when you do boxing. So, you have here, there's different, and we said, can we decompose them? Can we have an alphabet? That is, maybe you have here with a certain spike, here it's sharper, here it's less augmented, here it doesn't go to the same baseline. And we tried to do this, and we said, maybe, there's a continuum of these. So are we going to find them if there is a diversity, if I cannot even capture them by having 1 or 2 or 3 or a certain number of finite parameters? How do you find them? We saw that an alphabet will be enough. And we can, recompose them. We say, this is the sum of the two. Then we can play with L1 and L2. Maybe we can stretch L1 and L2 and say we can do a synthesis. We can change, multiply by alpha, multiply by beta, change the amplitude, and maybe we get. It was not working. Not working, just not working. It was too hard. It was not the right way to represent these features. Okay, so after some times, we say, why don't we use this EMD decomposition? What would that bring? The idea was that if you have a spike is something that, as you remember from the Gibbs phenomena, I explained to you briefly at the beginning, the Gibbs phenomena show that when you have something sharp or discontinuity, you have oscillations, which mean that it can be represented in multiple frequency. And by doing this, the idea is that if you have this, maybe the spike here will spread in different decomposition, in different levels. It doesn't just exist at one level, it will persist across the scale, across the decomposition. And maybe this is a signature, without going to go and try to understand the motif itself. So that's what we did. So you remember, you get here, so you remove the first component, and you get something flat, something that was oscillating, and suddenly you see appearing those events. Interestingly, those events persist across one scale and a second scale. And then we will continue this. You'll see that you get still some events, some features at the third scale. And then after this, that's it. You have destroyed the motif. You have destroyed the structure. And that's it. You can, and then at some point, we decide to stop. There is nobody that can tell us at which moment you have to stop. You decide to stop. So that's the decomposition, and now you can formulate the problem of finding those graphical elements by saying, I'm interested in finding something that persists across scale. If I have a feature that persists across scale, this is something I'm interested in. Which is a different point of view, because suddenly you are interested in a motif that is persistent, and you are interested in when it starts, when it ends, and you can count them by, for example, looking at the maximum. So here, for example, this is we had here 1, 2, 3, and 4 spike and wave. You see this little spike and wave, spike and wave, spike and wave. It's a bit hard to see, right? You do the decomposition, and you see them appearing like this. It's magic. Don't you think? It's magic. You see things that are so clear here, that are not that clear in here. So you see the power of signal processing in terms of finding features that are relevant for medical application. Okay, so that's what we did. We say, all right, I just implemented what I just discussed to you. We saw that you had the power. You look at in these 2 and 3 layers. We say, oh, look, we have something that is persisting across 2 scales. This must be something that we're interested in, and we're going to quantify them automatically. And how you can quantify them, it's clear. You can define a threshold. If I'm a certain threshold, okay, you're going to miss some, but if you say that at least I want to have in a certain time window, if I have at least 3 or 4, that's what I'm interested in, and then I can do automated analysis. Okay, I think we'll stop here for today. I showed 2 things. Fourier analysis, the Fourier power, and empirical mode decomposition. Next time, I show a bit of wavelets, and how do you remove artifact from a signal. And that's it for signal processing. It's important for me to show you this, because each time you deal with a signal, you have to understand what tools you are using, why this is important, what it brings. At least I cannot show you a full perspective, but some of it.